Related rates problems are, as you would imagine, problems that have to do with relating different rates of change to each other. So these are word problems, typically about some kind of situation where, of course, things are moving or changing, and we want to know how fast they're changing with relation to each other or at a specific point in time. Okay? So I have put an example on the board. This is a fairly simple one. Typically the difficulty with people have with these is just the same problem that people often have with word problems. How do I set it up? What am I doing? How do I set it up? So I'm going to go through a couple examples, and then we'll give sort of a general strategy, and then we'll just go through more examples, because the more of them you do, the more it'll be clearer what to do to set it up and what you need to do to get to the answer. Okay, so this problem is a problem about a balloon. A hot air balloon rising straight up from a level field is tracked by a rangefinder 500 feet from the liftoff point. Okay, at the moment the rangefinder's elevation angle is pi over 4. The angle is increasing at a rate of 0.14 radians per minute. How fast is the balloon rising at that moment? Okay, so we can just, first thing, always draw a picture, give things variables, and see if you can figure out like what the thing is even asking, what information is in the problem, and what information we're trying to actually find out. So let's draw this. I've got a balloon, hot air balloon. All right, so there's my hot air balloon, and it's rising straight up from the liftoff point. And the rangefinder is over here, right? So I've got a triangle situation going on. Now, they told me that the rangefinder is 500 feet from the liftoff point. So this length is 500 feet, and that length isn't changing. So that's an important thing in this problem. This length is the same. The rangefinder isn't moving. This one is moving only straight up. So you have two lengths that are changing here. The distance here and the distance there. What they really want to know about, though, is this distance, because it's asking you how fast is the balloon rising. So this is the information. I'm going to call it h, or you could call it y, but I'm going to call it h, right, because it's the, height of the balloon. So this is the information that they're really interested in. We could give this a name, but we'll find we don't actually need to use it. The other thing they're talking about is an angle, right? The rangefinder's elevation angle. So that's this. That's theta. Okay? So we have some variables on the board. And so let's write down what those variables are. So theta is the angle of elevation. And h is the height of the balloon. But there's more information in the problem, because they're not actually asking for h. They're asking for how fast is the balloon rising. So that's a rate of change. So that's dh dt. How fast is the height changing with respect to time? So that's why this is calculus, right? Because a bunch of derivatives. The idea is, as this balloon rises, all these quantities change. H changes, this distance changes, theta changes. The only thing that stays constant here is this guy, right? Because that's not changing, right? However, these other quantities, specifically h and theta, are changing. They're changing with respect to time. So what we do is we think about them as quantities which are dependent on time. So if I want, I can really write this as theta of t and h of t. So I think about the variables not as dependent on each other, but both as independent, well, related. Obviously, there's a relation between them, but they're both changing with respect to time. Okay, so that is sort of the key for all of these related rates problems. Because you're interested in changing with respect to time, you're going to take the derivative of everything with respect to time. Because that's what we're doing. I mean, Okay, there's probably one or two that we'll talk about next week where it's changing with respect to something else, but for the majority of them, it's changing with respect to time. So certainly this week, for the more straightforward ones, that's what we're looking at. Okay. So in any case, so what else are they talking about here? Okay. So theta is the angle of elevation, h is the height of the balloon. The rate of change, the derivatives, right, d theta dt is going to be the rate of change of the angle. So I can write it as rate of change of the angle theta. And dh dt is going to be the rate of change of the height. So if you look at what they're saying, the rate of change, they are talking about a specific moment in time when they gave you these numbers. There's numbers in the problem too besides the 500. The 500, I stuck it here on my graph because the 500 doesn't change. The 500 is constant no matter what time it is in the problem, right? But these other numbers change, right? The balloon goes up, so theta starts at 0 and it goes up as the balloon goes up, the height goes up, right? So those are changing. So what they're asking for is at the moment when theta is pi over 4, what is the rate of change of the height? So they want, so it says how fast is the balloon rising at that moment? So what they want is, the question is dh dt at the time when we'll put when theta equals pi over 4. Okay, so that's what we need to find out. Now, this is the trick with these, okay? You don't put in any numbers till the end, unless they're numbers that don't change with respect to the problem. Because dh dt, d theta dt, and theta are all maybe changing, right? So you don't want to put in the numbers until all of the derivatives are done. So what I need is I need a relationship between these variables h and theta. Then I need to take the derivative of that. That'll give me some information about the rates of change, which is what the problem is asking about. And then I put in the numbers. So it's like a couple of steps process. If you do it in the wrong order, then you'll lose information. So that being said, what's the relationship between theta and h? Well, it's easy, right? Because I have theta, h, and 500. So tangent. Tangent is opposite over adjacent. So right for my triangle, I have tangent theta is h over 500. Or if I want, h equals 500 tangent of theta. Now I think about both h and theta are functions of t. So if I want to talk about the rates of change, I have to take the derivatives of both sides of this with respect to t. So it's an implicit differentiation, right? Because I'm not taking the derivative with respect to theta or h, I'm thinking of them as sort of, they're both with respect to t. So taking the derivative of both sides with respect to t, right? So this side is just h by itself, so that's easy. That's dh dt. 500 goes out. Derivative of tangent is secant squared theta. And then d theta dt, right? Because it is an implicit differentiation with respect to t. So whenever I take the derivative, I'm going to get a d dt of whatever the quantity is. Okay, so I have to remember that I always have to get those rates in there, but that helps me solve the problem because now what do? I now have solved for what dh dt is in terms of other information, but they gave me that information in the problem, right? It's up here. So they told me that when theta was pi over 4, d theta dt was 0.14. Okay, so let me erase this for a second. And I'll just write that specifically. What they have here, when theta equals pi over 4, d theta dt is 0.14. Okay, so then I can solve for dH dt. I can put those numbers in there. dH dt is 500 times secant squared of pi over 4 times 0.14. Okay, so secant of pi over 4 is root 2. So, because it's 1 over cosine, so this is going to be 2. So this is 1,000 times 0.14. So this is 140. Now, it's 140 what, right? These all have to have units in them because they're word problems. So, but let's see, we have feet, right? Because dH dt is the change in the height versus the change in time. So the units given, the 500 is in feet, and the time given is in minutes. So feet per minute is my correct unit there. Yeah, so the business, like, then you could do like a whole units thing, but you can just sort of work it out there. So here's your feet, and then this is minutes, and then secant, you know, will give you a number with the radians. It's going to be the bottom. Anyhow, so there's my answer. Okay, that is the derivative of h with respect to t, or how fast is the balloon rising at 140 feet per minute.